So, starting from my right and progressing towards the screen, we have Sophie Bender, Jareth Deasis, and Emery Chesley. Today they're going to be presenting on main belt comets. Their mentor for this project was Henry Shea. Yes, and he's sitting in the back.
Hi, my name is Emery Chesley. Oh yeah, huh? Oh, sorry. So our presentation is on main belt comets, and the question is whether they're comets, asteroids, or both. So why should we study MBCs? There are a lot of reasons, but some of the main ones are MBCs could be a really good source of water in the future when we run out. And also, since MBCs are pretty old, like really old, like they've been around since the creation of the solar system, we could study them to learn more about the creation of our solar system and other solar systems. MBCs could also help us get answers about where Earth got its water. So, I mean, they're pretty interesting.
So, covering the basics, comets have tails. They have a very low density because they're composed of mainly ice with a little bit of rock and dust in there too. They originate in the Kuiper Belt and Oort cloud in the outer solar system. People believe that they are left over from when the outer planets formed, and they have elliptical orbits speeding up when they near the sun.
Okay. And the basics about asteroids is they don't have any tails. They have a higher density because they're mostly composed of rock and various metals, and they originate in the main asteroid belt, and we believe them to be leftover objects from the formation of the inner planets, and they have a circular and stable orbit.
Okay, so this here is Comet Hale-Bopp. Did I? Yes, I did. Okay, so you can see, we can tell this is a comet because it has tails, and not only does this comet have a tail, it has multiple tails. One of these tails it shows the comet's orbit. It is behind where the comet is heading, and the other is directly opposite from the sun. The sun's energy is pushing dust off the comet. This is asteroid 21 Lutetia. You can see it's it's very rocky, nice rocky composition. It doesn't have a corona or a tail or a coma or anything like that. It's pretty much rock and nothing else.
So, MBCs are kind of a cross between both. MBCs have tails, which would make it easier to find. We don't know a lot about their densities because we haven't actually had a real sample on Earth. But we're believing that they're kind of in between comets and asteroids because they have components of both. And they originate in the main asteroid belt, which would make that the third known source of comets in our solar system besides the Kuiper Belt and Oort cloud. And they have circular orbits like asteroids.
Okay, so what we believe about MBCs are they're similar or looking to asteroids in their rocky structure, and they have volatile portions of ice just beneath its surface, and also that they're in portions of the asteroid belt that originated from a larger body that may have stored ice, and they're in high collision areas, most likely a chip off the top layer of rock and expose volatile ice spots underneath.
Okay, so now getting to our experiment. In our experiment, we received photometric data, which is pictures, from our mentor, Dr. Henry Shea. He's back there. And the goal of this experiment wasn't to find new MBCs, but to familiarize ourselves with how they look on pictures. So we got 20 sets of 4 pictures each. All of these sets of 4 pictures were all in the same comet, and they were time lapsed. We entered these pictures into a program called Myra. Myra is really nice. It did everything for us. It centered them on the object. It combined them together so we could see the tails more easily. And we used that to find the 3 comets out of the 20, the 3 asteroids out of the 20 that were actually comets. And it wasn't that difficult. I mean, we had some problems, but Myra really helped us out, and so did our mentor.
So, like Emery said, we had 80 images, 20 sets of 4. 3 of them were NBCs, and we found all 3 of them in roughly 3 to 4 hours. We had a little bit of trouble with keeping the image centered and with cosmic rays and things like that, but we sorted them all out. And we used archive data because if we took raw data and found our own, we would not have been able to get it done in our time frame.
Okay, so from our observations, we were able to conclude 3 things. That MBCs have distinctive structural features which makes them visually unique. And we have more questions than we do answers about main belt comets or MBCs. And we learned how to use specific software and websites to acquire data about this search for MBCs.
Okay, so these here are a few of the MBCs that we found using Myra. Well, we identified. Okay. You see right there, that's the object, and upon closer inspection, we see that it actually, you might not be able to see it, but it has a tail, and it's very faint, but it's there. Trust us. We saw it. This is a little easier, but this is Comet LaSagra. Okay, I'm sorry. This is Comet LaSagra, and you can see it has a much more pronounced tail. This is Comet Elst-Pizarro. This was the first MBC ever discovered. And you can see the object is right there, and you can see the tail extends all the way down to there. So it's a very long tail.
Okay, these are some of the plot charts that we had, and this shows the inclination and the semi-major. So inclination is actually the tilt of the orbit of the comet or asteroid. And then the semi-major axis is how far away it is from the sun. And most of them are around 3.1 AU, and most of the objects that we found were around close to the 0 inclination.
Okay, this is a graph a lot like the previous one, except instead of inclination, thank you, we have eccentricity, which is the how elongated the orbit is. So if it's a bigger number, it's more elongated, more ellipse-like. And you can see that we have pretty much the grouping is pretty standardly around 3 AU, but the eccentricity varies widely. So originally we thought that they would be around a single eccentricity, but we were wrong. And that is why we do experiments.
Okay, so because NBCs were just recently discovered, we still have a lot of questions. So we're going to continue to get more data on them. And if we were to find a new one, because there are only 5 NBCs discovered so far and roughly 500,000 asteroids, it would be the equivalent of discovering 100,000 asteroids, increasing by 20%.
Well, our final slide, we'd like to say thank you. Thank you to our mentor, thank you to Ms. Katawoka, thank you to all the volunteers. I'm sorry. And thank you to you guys for sitting through that, and we hope you enjoyed it.
So I think we have time for 1 or 2 questions for each group before they sit down. So any questions from the audience? Yes, Mike. Mike
So,
Cross.
so in your images, how did you make them so that you could kind of capture the comet in a single frame? Why did it seem like everything was stretched out?
Oh, we had added the images together. We had combined them so that you would see all the stars and things that we weren't really tracking would appear as dotted lines. And because we were centered on the comet, then the comet would appear more detailed because we would actually see it clearer because it was several images.
Other questions? Okay. All right, great. Let's thank our group once more.